Alright, so in this video I'm going to be showing you how to do problems on the plane friction worksheet. You got 10 of them to do, and I'm going to go through one with you to show you step by step what you're supposed to do. It says using the following figure, fill in the chart, show all work on a separate sheet of paper and staple to the back. Calculators are allowed, but write out all steps. If needed, round your answers to two significant figures, pass the decimal point, no fractions or radicals, draw the free body diagrams for all problems. Don't forget your units. So we'll start off with problem number one. Let's talk about the situation. We've got a book or a block, whatever you want to call it, on a table, and basically what's happening is we are going to hook a LabQuest to this, and we're going to read how much force it takes to make that block move. And that is recorded right here. That's given to you, as is the mass of the object. So I've gone and found the mass of each of these objects, and then I went and pulled on them, and I said it takes this much force to move it, and I want you to tell me the coefficient of friction between them. Okay, so in problem one, we're given a couple pieces of information. Notice problem one, let me set up my papers here, is the first row across there. Okay, so problem one, we're given that the object has a mass of 0.5 kilograms. We are also told that if we pull with a force of 5 newtons, that's the point of sliding. So that's our big clue there. That's when it starts to move. So that obviously tells us the force of friction right before it slides is probably also 5 newtons. So as the instructions state, let's start with drawing a free body diagram. Here is our object, whatever it is, drawn as a square box. Our center of mass, we have the force of gravity pulling down, and they tell us that we are pulling this way with a force of 5 newtons. So first thing we're going to do, calculate the force of gravity. The way we do that is the mass times the acceleration due to gravity. In this situation, our mass, so we look right up here, 0.5 kilograms times, scooch over just a little bit, 9.81 meters per second squared. And so the force of gravity acting on this half a kilogram mass, I'm going to now punch it in, 0.5 times 9.81 equals 4.905. So this has a force of gravity of 4.905 newtons pulling it down. I'm going to box this in because this is one of the answers that we are looking for. If we go back to our worksheet, question number one, what is the force of gravity? So I can write 4.905 newtons there. Oh, I should have been 4.91 because we're rounding to 2 decimal points. So the next little box just wants us to change the units and change that into pounds. So the easiest way to do that is I look right here. It's given to us that this is 1 pound is 4.4 newtons. So if I have 4.9 newtons, it should be just over a pound. So the way to do this mathematically, I'm going to start with 4.905 newtons. That's what I'm given. And in 1 pound, there's 4.4 newtons. Newtons are going to cancel out. So 4.905 divided by 4.4 gives me 1.11 pounds. So just a quick reminder, in order to change from newtons to pounds, all you have to do is divide by 4.4. So I'm going to go back to my sheet, 1.11 pounds. Okay, so if I have a force of gravity of 4.905 newtons, our normal force is the table pushing back up. Since this block that we've got here is not moving up, not moving down, it's not accelerating, we can assume that the vertical forces are balanced. The normal force therefore must also be 4.91 newtons. So we can plug that number in, 4.91. We said we pulled with a force of 5 newtons, and if it's right at the point of sliding, then that also tells us that the force of friction should be 5 newtons. Force of friction is 5 newtons. Okay, so we can come back up here, 5 newtons. You're going to figure out that there's a lot of little tricks that makes this go very quickly as you work through this. And the last thing we need to do is we need to calculate for mu, the coefficient of friction, so we can tell how sticky that object is. So if I scooch my paper down here, to calculate that, the force of friction is mu times the normal force. There's our fun equation, F-U-N. I'm going to plug in the things that I know. The force of friction, I look back up to my free body diagram, was 5 newtons. And that's equal to mu, which we don't know, that's our unknown right now, times our normal force. I look back to my free body diagram, and the normal force was 4.91 newtons. If I'm solving for mu algebraically, I need to get it by itself, so I divide by 4.91 newtons. And what you do to one side, 4.91 newtons, you got to do to the other. Now I go to my handy calculator, and I'm going to do 5 divided by 4.91, and that equals 1.0, and I'm going to round this to 2 because it's 8 there. So 1.2 equals mu. I'm going to box that in just because I want to know exactly what everything is. I'm going to box this one in. All I've got to do now, go back to my sheet, and I'm going to plug in 1.02 as the answer for the first one. Now I'm going to move down and do number 2, 3, 4, all the way to 10. One thing that I want you to look at as you're working through these is as you move through questions 1, 2, and 3, the pulling force stays the same, but the mass increases. So you can start to sort of guess what do you think is going to happen as we increase, if more force is required to get it to move, or if the same force is required to get it to move, but it's a larger mass. What do you think is going to happen to the coefficient of friction? And then we bump our force up. See what do you think is going to happen if it now requires more force, but you also have to account for more mass. And so these things, some of them are the same, some of them change. It's just trying to get a feel for what happens as we change the pulling force and what happens when we change the mass. So again, there's all the work.